Hello, I'm Victor Raymond,
I'm Adrian Chavez.
And I'm Larry Hernandez.
and we're going to talk about our gearbox design for an automated factory.
The requirements for our project, this gearbox that we designed, is to have a 19-to-1 gear ratio, transmit 6 horsepower, our input RPM is 1520, and our output RPM was 80. Had to be high precision, and the cost was not a factor. After our initial calculations and looking through manufacturers' catalogs, we ended up with a 4-stage gear train with the teeth for each gear that you see up top, and the load calculations for each gear seen here in the middle. The 400 foot-pound of torque at the end there, it's pretty significant, which kind of eliminated a lot of the other gears that we had in mind when we first started out. The gears that we actually selected, also part of this design was it had to be high precision, so we ended up with helical gears from both Boston Gear and KHK. And these are the part numbers and the gears that we selected. After getting the initial calculations from the manufacturer and selecting our gears, we use the AGMA equations for bending and for contact stress to figure out whether the equations matched up with what the manufacturers presented in their catalogs. For the most part, they were fairly close. We did find some discrepancies for a couple of the gears, and a lot of it might have to do with the material selection that we actually put into the AGMA equations versus what the manufacturer actually uses for some of them. Finding that information is sometimes tricky. So some of the assumptions that we initially put into the AGMA equations were where the discrepancies are.
So after we calculated our gears, we began analyzing our shafts. The maximum shaft length we had was 6 inches. So as you see here, we took that 6-inch shaft and we put it into SolidWorks to figure out what our loading would be. We began by fixing one end of the shaft and applying load to the singular tooth that all these gears use to bind to the shafts. Technically, they have a screw that locks them into place, but we went for worst case scenario in which that screw backed out and was not providing anti-rotational support. So if you can see here, the load was applied directly to the tooth of the max load that was calculated for any gear set. With this, we still came out with a factor of safety of 1.2, which was way above what was expected during its normal operation life.
The final process would be to select bearings. Using the maximum force applied of 400 foot-pounds, we figured the life of the SKF bearings was 12,000 hours and 1 million revolutions. Using that, we found the C values, and then we sourced the bearings. These are the part numbers for the bearings, are the RMS8 and RMS82Z, and they match up to the maximum C value in pound force.
So a big part of our project is cost. And another factor to consider when you're talking about cost is either if it's a single purchase unit or if it's a bulk order for mass production. As you can see here, we have a compiled list of prices for both a singular unit and a bulk order unit. And if you see here, the difference is really large between the two of them. In fact, the bulk purchase actually comes out to be less than half of what a single unit costs. This is due primarily to the housing. We contacted several CNC companies and found that if required to mill out a housing such as ours, what we would need for our bearings, it would come out to be about $2,000 for all the work. However, if we went onto a mass production option, a mold could be cast and used over and over again, and then that way it would cut the cost down to approximately around $500 per unit, which is a big discount on price. Also, the gears themselves are about a 40% cost reduction when ordered in quantities over 1,000, which is a lot of savings. So as you see here again, the cost for a fixed unit is about 4,000, and the cost for the bulk order unit per unit is about 1,700. 1,800 is a standard for many units in the industry of the same type of setup with gear Same type of gearbox setup.
Here you're seeing the mesh of the first pair of gears, the 12 and the 32 tooth. Then you have the 15 and 36 tooth, 20 to 60. And finally the two idler gears, which are just used in order to maintain the rotation in the same direction as the input for the output, which was also part of the requirements of this project. This is a rendering of the final gearbox and a short video of the gearbox in motion. The yellow canister is actually supposed to be electric motor, and you can see the gears in mesh actually meshing with each other and spinning there, working together. You have your 1232, your 1536, your 20